AB Calculus Note Card 3, Analytical Strategies for Finding Limits. This is the third video in the Note Card series that was inspired by Stacy McMullen, formerly the Dallas Independent School District, who I was trained by in 2 summer sessions, as well as by her mentee, Tracy Etheridge. Anyway, here we have analytical strategies for finding limits, and we just have a list of different things to try. And as you become familiar with the things in this list, what happens is more apparent. First, try direct substitution. Second, try factoring, then canceling, and see what we have left. Third, try a special trig limits, and we have 2 specifics. This first one here is really more common. Okay, the sine x over x, than this cosine one. I'm going to get a skinnier pen here. Okay, and then the fourth one, the limit may not exist. The function is unbounded, oscillating, if the limit from the right does not equal the limit from the left. And then we have, as with all these note cards, some examples with them. And there are 9 little problems I'm going to work out demonstrating the techniques here. Well, the first one is try direct substitution. And so the limit as theta approaches pi of theta secant theta. Well, what we're going to have is we're going to try direct substitution. So to do that, we're going to say, okay, we substitute pi for theta. So the theta is replaced by pi. And then so we have pi secant pi. Okay, well, secant, I don't know if you remember this from pre-calculus, is 1 as the reciprocal of cosine. So in this case, we're going to have pi, and then we're going to have times 1 over cosine pi. Well, cosine pi, that's going to be over there at 180 degrees, is going to equal to -1. So what we're going to have here is pi times 1 over -1. And when we work all this out, we're going to get negative pi. So our answer to this limit here is going to be negative pi. And we used technique 1. We tried direct substitution, and that's that. The next one we have here is the limit as x approaches 1 of x squared plus 5x minus 6 over x minus 1. And the first thing we're going to do is we're going to try direct substitution, and when we do that, we're going to have 1 squared plus 5 times 1 minus 6. And then here in the denominator, we're going to have 1 minus 1. And we work this all out, we have 0 divided by 0. And I tell my students, whenever you see that, what you have here is something we call more work. Okay, so that's called the indeterminate form. And in step 2 here is try factoring, then cancellation. So we're going to try factoring here. And to factor this, we're going to have, and what I'm going to do is I'm going to write out the whole thing. We're going to have limit as x approaches 1, and then we're going to factor what's in the numerator the denominator of x minus 1, and in the denominator of x minus 1, the numerator, we're going to have x minus 1, and what times x minus 1 is going to equal x squared plus 5x minus 6? So it's going to be x plus 6. And then we can cancel here. And so what we're going to get is the limit as x approaches 1 of what's left in the numerator, which is x plus 6. And that's going to be equal to 7. So our answer to this second problem is 7. Next, problem 3. We're going to try direct substitution again. And when we substitute directly, we have 1 in the numerator. In the denominator, we have 0 squared. Now, in this case, we do not have 0 over 0. We have 1 divided by 0, which is going to be undefined. And so we say the limit as x approaches 0 of 1 over x squared, we say that limit does not exist, which I abbreviate DNE. It is not equals does not exist. It does not exist. Okay, 4. If a is not equal to 0, then the limit as x approaches a of x minus a over x to the 4th power minus a to the 4th is, fill in the blank. One thing we have in these problems I want to make you aware of, where we have these asterisks here in these note card problems. These are problems that came from actual AP exams. So what we're going to do is, if we substitute in x for a, if we let x equal to a, we're going to have a minus a in the numerator. In the denominator, we're going to have a to the 4th minus a to the 4th, which will give us our infamous 0 over 0. And so what we're going to do is we're going to try factoring. And to factor, we're going to have, I'm just going to write it in limit form, limit as x approaches a. And in the numerator, we have x minus a. In the denominator, we're going to use a difference of squares. And using the different squares, we're going to have x squared minus a squared times quantity x squared plus a squared. Okay, well, can we, if we go ahead and substitute in, we would still be stuck in the same situation with a 0 over 0, because this would factor to 0 and this would we'd have 0 over 0 still. So we're going to try to factor one more time in the denominator. So you have the limit as x approaches a, and we maintain our numerator of x minus a, but our denominator, we're going to be able to factor this quantity x squared minus a squared into x minus a times x plus a, and then this quantity x squared plus a squared is not factorable. Okay, we cannot factor that. So let's go ahead and cancel what we can. This x minus a over x minus a cancel, and what we have left is substituting in x, a for x. We're going to have 1 in the numerator. In the denominator, we're going to have a plus a, and then we're going to have, substituting a for x, we're going to have a squared plus a squared. And what that's going to be equal to is 1. And this a plus a here is going to be 2a. And this a squared plus a squared is going to be 2a squared. And we multiply all this together, we're going to get 1 over 4a cubed. And that's going to be our answer. So we'll say 1 over 4a cubed. Okay, so that's going to be number 4. Number 5, find the limit as x approaches -4 of r of x if r of x equals 2x squared minus 3 when, and you see this piecewise function, sometimes you'll see a comma on each of these, when x is not equal to -4, and 1.7 when x is equal to -4. So what that's going to look like is, I'm just going to graph it over here. You have this function. I'm going to graph this function as well as I can. You have 2x squared minus 3, and so we're going to have our y-intercept of -3, and so the function is going to look something like this. A quadratic function. It will look something like this. And when x equals -4, if we go to -4 someplace, we know that we have 1.7, and then it's this function everywhere else. And so this everywhere else is what determines the limit. And so our answer to this is going to be plugging in -4 for this top piece here. So we have 2 times -4 squared minus 3. And that's going to be -4 squared is 16, and 2 times 16 will have 32 minus 3 equals 29. So that's going to be our answer here, 29. So that's number 5. Number 6, the limit as x approaches 0 of sine 5x over 2x. And if we substitute in, if we try substituting, we're going to get sine of 0, which is 0, over 2 times 0, which is going to be 0 over 0. But let's go back here. Do you remember what I circled here, the special trig limits? So we have sine x over x equals 1. And so what we're going to be left with here is 5 over 2. And that's going to be our answer, because sine x over x is 1, and so we just have the fractions left here, 5 over 2. So 5 halves is our answer. Next, 7, limit as x approaches pi over 6 of cosine x. So we're going to try to substitute directly, and the cosine of pi over 6 is going to be equal to square root of 3 over 2. And that's one of the values in the 16-point unit circle that you should know at this phase in your calculus career. So this is our answer, square root of 3 over 2. Okay, next, 8. The limit as x approaches 0 of absolute value of x over x. And what we have there is just graphically what this looks like is we're going to have, we have an XY coordinate plane. That's not very attractive, XY coordinate plane. What you're going to have is, to the less than 0, this x value is going to be negative, and this value on the top, this absolute value of x, is always going to be positive. We're going to be undefined where x equals 0, but we're looking for the limit. And so if the function is, if we have a negative divided by positive at less than 0, we're going to have a horizontal line here of x. We're going to have y equals -1, and up here in the, as we continue to the right, where x is greater than 0, we're going to have this. We're going to have y is equal to 1. And so we say that the limit for this, and I'm just going to write it down like this, limit as x approaches 0 of absolute value of x over x does not exist. And why does it not exist? Because if we look at our earlier note card, I believe it was note card 2, it was the left-hand limit has to equal the right-hand limit for a limit to exist. And we see that we do not have, we see that the -1 is not equal to 1, therefore the limit does not exist. The last one we'll look at, 9, if g of x equals 3x cubed minus 5, then limit as x approaches 0 of g of x minus g of 0 over x to the third power equals what? What we're going to have here is we'll say, I'm just going to write the limit down here, limit as x approaches 0 of g of x, and I'm just going to write g of x here, which is going to be 3x cubed minus 5. It says minus g of 0. Well, minus, if we plug in 0 here, we're going to get -5. So minus -5. And that's going to be over x cubed. And so working to the right, we're going to have -5 minus -5. We're going to have limit as x approaches 0 of 3x cubed over x cubed. And if we substitute in, you can see that we're going to get 0 over 0, right? If we substitute in, try direct substitution. But fortunately, we are able, the x cubed over x cubed will cancel each other. So we're going to have, that's going to be the limit as x approaches 0 of 3. What we have left 3. So our answer to this, we plug in 0 for x. We don't have an x here. Our answer is going to be 3. So that's going to be our answer to problem 9. So these 9 problems were different examples of the use of these 5 techniques, these 5 situations. And this situation number 4 was in evidence here in problem 8, where the left-hand limit does not equal the right-hand limit. So anyway, this is you're going to get from your teacher a lot of other examples, a lot of opportunities to understand what's going on here. Good luck, and thanks for viewing.